Okay, ladies and gentlemen, welcome to our second lecture from data analytics. We'll focus today on Bayesian Basics. I've tried to update the visual side of the slides, so hopefully they will be more legible and more configurable. So like the thing that I'm losing the most time is preparing nice figures, so they will be working and they be replicable, because it's easy to make it in a graphic program and then not being able to edit it. So I try to everything to be more or less replicable. Today we will focus on the main concept of Bayesian statistics. So we'll discuss certain concepts that we'll be using for different types of computation. Then we will move to single parameter models. We'll focus on binomial distribution. So we will be analyzing how to create such models, and how to investigate them on different aspects. Single variables are simple because of many reasons, but soon we'll realize that there are issues that are not generalizable. And then we'll discuss the priors. Prior selection, how to, what kind of priors we have, and we'll try to do an example considering different types of priors and what we can do with that. So, as previously, we derived the base rule in order to determine that the conditional distribution of parameters conditioned on measurements is our posterior probability, so it joins our a priori knowledge, prior, and the data that we've collected. Prior distribution is a probability distribution that corresponds to our state of belief about the values of parameters or probability of hypothesis that we are considering, or multiple different stuff. The prior, as I've mentioned before, has certain aspect of subjectivity to it. We assign the prior based on our belief or our knowledge, and we need to do a modeling selection how to create that prior. And those choices are not necessarily 100% objective, that there is one prior that ends it all and represents everything. There are situations that it's obvious that this prior is good justification, and some situations that usually artificial problems, and in real life problems we usually use priors that give us some kind of advantage in computation or knowledge representation that we want. Likelihood, on the other hand, is the function that represents how well our data corresponds to our model. So likelihood represents our model and encapsulates us how the corresponding to our parameters, our model is represented. This is very similar to something that we already know, some kind of performance indicators that we've used in optimization, something like that. In this case, however, likelihood function is generally a function, not a single value. Performance indicators were values that we wanted to, for example, minimize. In case of likelihood is a function. We can correspond it, let's say, to a performance indicator function that gives you a value corresponding to how well the data corresponds to our model. And again, selection of likelihood is important in order to represent our problem. Usually, for example, if we want to create a model that represents our process as a normal distribution, that, for example, our data come from a normal distribution of, let's say, people's heights or something like that, then our likelihood model would represent this, how well our data fit the normal distribution. Usually it's done by using the same function as the distribution. That is, in this case, would be one measurement minus expectation of interest, that the parameter of first of the parameters of normal distribution divided by the Second parameter is standard deviation, and that's squared. So that's the point. And as we mentioned before, in case of Bayes' theorem, there would be also a denominator that was a total probability of data, or in other words, it was the averaged entire numerator for all possible values of theta. This, however, is a number, because we have a fixed number, fixed data, so getting to that really it would be a number. So it's only switches moves the prior as a proportionality constant, which is why we are using the symbol of proportionality here, this one, and the symbol of proportionality represents that we are interested in the numerator, and numerator is also enough for us, for example, to do some computation. If we would like to, for example, find a maximum of posterior distribution, numerator would be enough. Multiplication by a constant would not change our maximum value. But it's not something that we will be doing. However, numerator also is what should be important in a sense. It is also can be considered as a joint probability of both measurements and parameters. So measurements coming from the process and parameters characterizing the process. Because such multiplication is a definition of joint probability. Yes, but again, here up to a certain constant. Of course, we will be considering certain important parameters, especially important for all our computation will be expectation. Expectation, which we also know as mean or average, maybe not so precisely, is a function that it's a value that characterizes a certain probability distribution, which is an integral of probability distribution function multiplied by the variable and integrated by it. So this is something that you should already know. This is a very classical value of computation, and the mean of the sample is the expectation, is the estimator of the expectation, which will go to the additional one. Is variance, of course, is how generally how the distribution value of how the distribution is spread around its expected value. So those functions are very important for us. Just as a, let's say, spoiler, we won't be computing integrals analytically at all. Those integrals are present in our computation. However, we will not be computing them directly because usually it's not possible. Because integration is a task that is not as easy as differentiation, and but we will get those values using some kind of estimation of the expected values, or we will be using the formulas that are already available. Because everywhere we are considering conditional distributions, because we have the conditional, we are usually conditioning on data, we will be considering also in our computation conditional expectations. So generally, the main difference in it is that we will be, instead of u here, we will be using the expectation of u conditional on v. So such situation is the relatively simple aspect. As you can see here, we have the expectation conditional on v, and this is expectation of the entire variable. Again, not something that we will be computing directly. Those values we will be estimating, but we need to be aware that distributions are also conditional on the data or on different parameters. Because generally, in everything we will be thinking about, everything is conditional. Because creating a model is not happening in the vacuum. We are not getting some signals from the universe. Everything is based on our assumptions that we've provided somewhere. So every model we've created includes those assumptions, either explicitly or implicitly stated during our analysis. When we are using normal distribution model, we are, besides aspects of mean and standard deviation, we are assuming, for example, that values that are very far away from the expected value, from the mean, are very improbable. That's the behavior of normal distribution. When we are using binomial distribution, we are limiting our scope of variables to integer numbers and stuff, and all that everything has certain state of knowledge, certain hypotheses that we formulated as a background. So we will not be marking that in our computation. However, we need to be aware that all our computation, all our work is constrained to or is conditioned by our prior belief or prior decision about the process. And this is important because generally what we will be doing is we will be in many cases marginalizing certain parameters. This is an important aspect that usually our models that we stated before have observables and unobservable parameters. And not necessarily all observable parameters, unobservable parameters are of our interests. For example, we are interested in, let's say, what is the expected value of certain underlying process, but we are not interested on the characteristics of the noise. We do not want the individual probability distribution or joint probability distribution that includes that information, because that information is useless to us, and also we will not be using that in order to improve our prediction or our analysis. And on the other hand, in order to capture the entire process, the entire information, because we need to get those elements in our model. So our model will have multiple parameters, and those parameters will be, let's say, a nuisance to us. We a problem that we didn't want in our analysis. However, Bayesian statistics, because every parameter is a distribution, is a random variable, we can perform a marginalization of those parameters. So we can just integrate them out using the joint distribution of those parameters that we are interested, for example, joint posterior. We can integrate out of that the variables that we are not interested in. So in this case, we will get a bit more diffuse, less at point representation of θ1, but we will not have the relationship between θ1 and θ2. We just get that, okay, because θ2 behaves like this, we just get, like, we'll average out our posterior for all our, depending on where θ2 is more probable. And this, of course, can be, again, decomposed. So in this case, we will just get the θ1 conditional on θ2 and y, and probabilities of θ2 conditional on y. So we can get that integration. Again, this integral is not something that we will be computing directly. This is something that we will be able to get those marginal distributions of parameters rather easily through Bayesian computation in the future. But be aware that this, again, the process of marginalization is the averaging of everything that we are not interested in. So we, depending on the situation where θ2 is large, there are more θ2, those values will be more important in this average, that where there's less θ2, the θ2 values that are less probable, then corresponding to them values θ1 will be less influencing this final distribution. And special examples of those marginalization procedures are based on marginalizing the parameters all together itself in order to get some kind of information create some kind of predictions. And we have generally two kinds of predicted distributions. Probability distributions that samples from are representing our knowledge about data. First one is a prior predicted distribution. Prior predicted distribution is a distribution that allows you to predict what data is expected by your prior distribution. So we take our model that consists of likelihood and prior, and we integrate out the prior parameters out of it in order to get distribution of y from which we can sum. In practice, we do it all again by sampling. We do it like this, that we get random values of parameters from prior distributions. Then we put them into the likelihood function, which becomes, in a way, a probability distribution of y's. So we can, because then is only has numbers, it's probability density function of y, from which we can sample y's, and we get a sample of y. And we repeat this process: sample theta's, sample y's, sample theta's, sample y's. So we do not get the any data here, actual data. We only simulate data, and this is a very useful concept in order to validate our models. Do our models make any kind of sense? Because before we put any data to it, we want to see if our prior knowledge or method of encoding that prior knowledge is representative of what's happening. So, for example, if our model based on our prior information will result in values that are absurd, then something is wrong with it. Moreover, if our prior model gives us results that are completely inconsistent with observable data, there also might be some problem, that we might not be modeling something, or we may be creating some errors. So prior predictive distribution is a very useful tool in order to get how the model is working. Today we won't be doing that, because today we are not sampling, we're just doing some basic computation. But this is our first test tool for our models. Before we see the data, we can test from our model, is our model making any kind of sense, and will it be able to capture observed data. One of the tests is, for example, comparing the observed data with distribution of those simulated ones. If what we observe is somewhere in the bulk of distribution, then it means that it's probably okay. If it's completely different, then something is wrong. Either either experiment was performed in a way that, or the situation was completely unobserved before, so maybe the device is faulty, or we did experiment wrong, which is also possible, or we created our model wrong, which is the most possible. Because this is the first thing. If you see that your data are not working with your model, the first assumption should be model is wrong. It's not that reality is, we've discovered new laws of physics, it's that the model is wrong. There was, if you don't remember or not, there was a declaration from a science team that they've discovered that neutrinos are faster than light. It was a few years ago. And that was, they've proclaimed that, they published the paper, and after some time it was verified that the cable was bent somewhere, and that introduced enough disturbance, and when they corrected that, the results became more normal. So, unexpected things usually require further investigation. The complement to prior predicted distribution is the posterior predicted distribution. Posterior predicted distribution is used to simulate the data from the model that was already fed the data. So how our model captures the possibility to generate the data having the available knowledge. So generally, again, what we do, we marginalize the parameters that are now consistent not with our prior, but with our posterior. So we sample parameters from the posterior, and then, using those samples, we simulate data using likelihood. And getting the distribution shaped by the likelihood. This is not exactly the same. There are subtle differences, but nevertheless there are. So we sample from the posterior distribution and we generate data from it. Why is this useful? Because this gives us an answer how our model is, after learning, let's say, through providing it with data, is able to give us the actual data. Will it be able to replicate the process that was used to learn it? If yes, well, that's good news. That's good news because there is some consistency. If not, there is again something seriously wrong, probably with our model, because model doesn't correspond to the data. So this is again a very important main testing tool. It's our main validation tool that allows us to validate is our model, about consistency of our model. After that, after the validation, we can also use it in order to, for example, create predictions on the more advanced groups of data, or predict something that we want. This is a way of predicting next values knowing the previous ones. We had the data, we are now predicting the future values. And so this is the posterior predictive distribution. Again, no integrating by hand necessary. We are doing it through sampling. Next important concept that we need to focus on are the variable changes, because this is something that you've probably had on your first year of studies during probability theory course. But the problem is that probably variable changes are practically important. It's not that we want to just get the distribution of square root of a variable or something like that, because no, that's not something that we just want it like this. We, however, often find a situation that changing the variables requires from us certain additional, it's required for us in order to make the computation possible. And depending on what kind of distribution we have either the discrete or continuous distributions. In case of discrete distributions, this change of variables is very simple. The probability mass function, because for discrete we have mass functions, for continuous we have density functions. For probability mass functions, we just take the value of function and we replace the values of one variable with the inverse function of the other. That's okay. In case of continuous distribution, in order to get the formula for probability density, we need additionally to multiply it by the Jacobian, which we are using English definition of the Jacobian. No, we're actually using Polish definition of the Jacobian. Jacobian matrix, or Jacobi matrix in Polish, is the matrix of partial derivatives of a function. In case of, in Polish, Jacobian is the determinant of that matrix. In English, Jacobian is the matrix, and we can say that the determinant of that matrix is here. Either way, we need to compensate for the changes in this continuous function, so that's why we need to use this. And this is something that we rarely, but sometimes we need to do in order to get some kind of representation. Usually, we will be able to move through it through sampling. So sampling with values. However, we need to be aware that for example, if we try to compare analytic plots and simulated plots, there will be issues that need to be repaired by this. There are certain variable changes that are more important than another. Because of course, we are not speaking about linear variable changes because this is irrelevant. However, in certain cases, we generally, especially from practical point of view for sampling, we do not like bounded spaces. Bounded spaces are not very nice for us because bounded, as we will learn soon, the sampling of complicated distribution requires from us solving certain differential equations. The problem with differential equations is that they are very well defined on smooth manifolds or generally unbounded. We can think about unbounded spaces and do not make our life too difficult. However, when solution of differential equation approaches the boundary, there are problems. Because existence of that solution is complicated analytically, and numerical solution in that way that how to move from this onto this, or should it move through the boundary, or should it bounce from the boundary? This is a very complicated problem. That's why we generally do not want the boundary, the hard boundaries. Moreover, often, for example, we want to use, let's say, linear combination of parameters with unbounded parameters, so we will naturally have certain values that are in the range from minus to plus infinity, so real numbers. And sometimes those numbers will have to represent something that is more limited, like probability or like positive numbers. And in such cases, we need to introduce something which is called a link function. So a function that will translate our values of our unbounded values to a certain bounded interval. This is the root of something that you've already heard about, generalized linear models. Generalized linear models are a method that create a linear model and then move it to the link function in order to get to the to be able to do some non-linear. And certain transformations are most popular. First of all is a logarithmic transformation, which is used to get from the plus minus infinity into the positive real values. Which is important, for example, when we have certain intensity of processes, like let's say we have a series of events that are happening with certain probability, and the number of these events depends on certain intensity. And this we don't have the anti-events, so this intensity cannot be negative, right? So this intensity must be positive value. However, we might want to represent it our knowledge, our predictors, using linear combination or non-linear combination of parameters, which might be unbounded. So we need to move it through a logarithm function. And more precisely, we want to use the link function that our variable will be a logarithm of something. So actually, we will be exponentiating those values. We're doing through the inverse. The most famous one that you've probably heard about and will have contact is the logistic function. This is the one that is used in classification problems or probability estimation problems, which is a function that is corresponding between minus and plus infinity to the 0, 1 interval. And a logistic function is generally a sigmoid function that takes real numbers, and if they are sufficiently big, they are squeezed either to 0 or to 1, depending on the sign. If they are small, they are moving around this nonlinear curve, right? So this is the logistic function. And logistic function is a logarithm of x divided by 1 minus x, and its inverse that we are using, so this logistic function moves from 0, 1, gives us the values of to minus and plus infinity. However, invologit, or expit sometimes called function, is the opposite. That gives us from minus plus infinity to 0 and 1 as you can see in exponent values is always less than the value will be always less than 1 and greater than 0, because exponent function doesn't take 0 for value. So numerator is always greater than 0. So at the limit it approaches 0, but it won't reach 0. And if y tends to infinity, exponent by is divided by exponent, so it is then this value is then limited to we can divide it by exponents, so those will be the ratio of them will be approaching 1, but always because of this 1 here, the numerator denominator will be always greater than numerator, so the result will be less than 1. And of course it's always positive because exponent function is positive. So this is the most used one for such translation, and we will be using it later. However, there is also additional function which is called profit, which is also used in certain applications for also transporting 0 and 1. However, instead of logit function, it uses the inverse of the standard normal cumulative distribution function. If you remember, if you had a standard normal distribution function, of course this is a function that again goes from 0 to 1 at from minus to plus infinity. The difference in this case between these two functions is that the probit tends to 0 and to 1 a bit faster. And because that logits generally tends to those as x to minus t, and the t squared. So this one just drops faster. So it has so-called lighter tails. So there will not be the values that are in the middle will be more concentrated. The issues with those functions is that while there are fully invertible and differentiable and generally rather nice, there still are issues that come from the fact that we are collapsing a very large piece of space of large to real numbers to a very small representation. So it can give certain numerical issues in certain cases, especially if we want to invert it later. Okay. Is this relatively clear? This part. Those we covered definitions, but I tried to give you the justification where they are used and what they are for. Everything is okay. So let's move to the simplest possible models, that is single parameter models. Single parameter models are very simple distributions that generally correspond to only one quantity, and they are not only educational because they are building blocks of more complicated models. So certain single parameter models will be used in many cases either as priors or as likelihood functions through transformations. So they are being used, and for example, applications of one parameter models is like what is the average difference between two groups, or how strong is the association between two, so like a correlation coefficient, or does the effect relies on certain variable or not, or how much, or just modeling variation between groups, or probability of the event, or multiple different aspects that are happening. And the most simple model that we can think of that will not give us much difficulties is the binomial model. Binomial model is a natural model from data that comes from sequence of trials. So sequence of events with some kind of binary outcome. Simple example, gambling, that we win or we lose, or COVID tests, or multiple different aspects that we can get to generally categorize results in a binary form. That's like a success or failure. Coin flipping, ball tossing, match winning, etc. In case of binomial model, we have very simple likelihood function, which is constructed using the binomial distribution. And this function checks how our values of theta in n trials corresponds to our model. And it is given by theta to number of successes and 1 minus theta to number of failures, so the results that are not a success, multiplied by a constant depending on number of trials and number of successes. Generally, this is a normalizing constant, not that important as we can see. So generally, having known theta, we get a function depending on y, which is corresponding to certain values. We can also use this, knowing theta, to simulate y's, because it can be used as a probability distribution. This distribution is very pleasant because it is concentrated on the 0-1 interval. If we have the, let's say, 11 trials with 7 successes, it will move to the, it will reduce the probability of the event. Well, here, the probability of the events of 0, so no successes, will be very small because will be vanishing, and of all successes will also be vanishing. So this is generally a polynomial of appropriate or of order 11 at this moment, with 7 roots in 0 and 4 roots in 1. And the shape of the distribution will be located relatively here. So this is easily computable. If we change the number of successes rises, then the probability of failure will be appropriately lower, and probability of success will be appropriately higher, and again and again. Analytically, we can see our Bayesian model in order to compute the posterior. For the prior, at first, let's take a most simple posterior prior. We do not know anything about theta. So, for example, we are testing a coin. Is it fair coin or not? Or we are testing a planet and we're looking for water. We do not know what the coverage of water is. However, we are dropping the probe on the planet, and it checks. There is water. There is no water. There is water. There's no water. So these are our results. We do not know a priori anything about it. For example, the planet is completely covered by clouds. Let's say even toxic clouds. Toxic clouds, so we cannot fly into it because the corrosion will destroy our spaceship. If we drop we can drop probe because the probe is not coming back, so it just needs to get to the surface and check there's water or there's no water. So, having complete ignorance, we assume that any amount of water on the surface, percentage of water on the surface is possible, right? So, uniform probability distribution for this case seems reasonable. We just are giving it's a uniform distribution. So our posterior generally is equivalent up to a proportional set to its likelihood, and moreover, such function, and this is the main conceptual concept that you need to follow here. This function, depending on how we look at it, is either binomial distribution or beta distribution. Binomial distribution is considered knowing theta what will be values of y. Beta distribution is knowing y, what is the value of theta. This is the same function algebraically with a correspondence to the certain constant. However, the understanding is different. So instead, we've started with binomial likelihood, and by doing nothing to it, we've turned it into a beta distribution. But what we did actually, we stopped thinking about, we've changed what is the variable and what is the parameter. For the likelihood, the parameter is theta and variable is y. For posterior, the variable is theta and parameter is y. Okay? You understand that? This is this posterior is a beta distribution. Why we are looking at it as a beta distribution? Because generally we have lots of books on probability theory when there's a lot of distributions. Summarize them, and some nice mathematicians have spent some time in order to compute appropriate functions for those, like what is the mean, what's the median, what's the variance, etc. So those certain moments of the distribution, those things are already computed, which give us enormous advantage because we are able to get, without much computation, without any integration, all those integration we've needed were done by us already. We just put the value, the parameters of the distribution, and we get values of interest. So this is an advantage. We also cover why it's not, but in a moment. So our posterior distribution is a beta distribution parameterized by y and n. It depends on the number of successes and the number of experiments, which generally here corresponds to number of failures plus 1. But this is the problem of data analytics, that having the posterior distribution is not a problem. In order to create posterior distribution, we need to know what is the likelihood and what are the priors. Then we've computed by it, and we have the function. We've multiplied one by another, we have a function. The problem with this function is that generally it is so complicated that we cannot compute anything of interest from that. We can compute individual values of the function wherever we want, but as you should remember from probability theory, the value of density in a point gives us nothing. In order to get a probability of an event, you need to get some kind of integrals over certain areas, right? If you want to get expectation, you need to get some limits. Perhaps you can, using values, you can compute the maximum, but it is very limited, which we'll cover next week. Why maximum is not? So, generally, we want to get some kind of information from our posterior to get some inference. Of course, posterior gives us a lot of information and we can plot it so we can see what's going on, but it is feasible for one-dimensional problem, right? If we have one variable, we can plot the posterior distribution and we can see, okay, the most probability is here. Because remember, human brain is the best processor of images possible. Looking at the function, we already see where's the maximum, where's the bulk of it, where are tails, is it positive, is it negative? Looking at the plot, we know everything. Computer, even having the same values that plotted as this function, will not know what to do with it unless we give it a special recipe for operation, right? We can, for example, infer what should be the values between samples, or will be the points, and computer will not. We have to give it specialized recipe. So human, okay, we can look, but even 2D graphs are complicated to interpret, and even more is worse. So usually we will get some kind of number. We want a number. Number is nice because we can give it that we got 7 and our opposing team got 6, so we are better. right? Or we get 99% efficiency and they got only 97. So winning, right? Usually we get some kind of value. Most popular values, especially for one-dimensional ones, are mean, median, and mode. Mean is the expected value. Mode is the maximum of probability density. Median is a point where half of the probability is on the left and half is on the right. Additionally, we want to get some kind of measure of uncertainty. In order to do so, we, for example, can use variance or standard deviation or interquartile range or other quantiles, so we get the information of distribution, where the bulk of distribution is, what values are most probable. And this is one option that we will often use because it's useful. So let's look at our distribution from before. Because we know beta distribution, at least I know beta distribution, you probably didn't remember that such distribution exists. Certain coefficients were already computed for it. Variance is horrible because it's a terrible formula, but the formula for the expectation is known. And this expectation conditional on the data. So it's a conditional distribution, conditional expectation of theta conditional on y is alpha divided by alpha plus beta, which is y plus 1 divided by n plus 2. But why? Shouldn't it be y divided by n? We've performed a lot of a series of trials. We had 7 successes and 11 on 11 trials. So why the probability of water being on the planet is, or the expected percentage of water coverage isn't 7/11, but it's 8/13. Why? What I will tell you more, the classical statistics, frequency statistics, would give us this result. It would give us y divided by n. So why Bayesian statistics, in this case, differs, let's say even significantly, in qualitative way from the classical frequentist result, even if this is a very simple problem. This problem is called the rule of succession. It was an experiment, tough experiment given by Laplace. What is the probability of if the sun would rise again next day, given that it's risen previously for multiple days? He was ridiculed by it, and generally there was big conflict in the debate here. But the main difference here, especially that, look at it, we have added the prior, which is uniform. So what happened here? The thing that happened here is that we've encoded additional information. In this case, the most important one. There are 2 possible results. Either there is water in the trial or not. This formula, and this one doesn't, has this advantage that it will also work in a situation when there are no experiments. This will work where n is equal to 0. It gives us ignorance of result, either water or no water, and that's it. Expected value in this case is half because it's the middle of the interval. If you compute the expectation of the uniform distribution on the 0, 1, it's exactly in the middle. This is the expected value. And Bayesian statistics encodes us information here in this prior because we've added the information that certain result is possible. So using classical result, if we had a series of successes, the probability, without any failures, for example, we would get only no water, the probability of water is 0. In case of this formula, the probability of water is small and is reducible, it's not 0. So there is possibly a justification at what level we can stop testing. When this probability is that that the chance is small enough. In this case, we get one success or a failure. We do not have any justification of when to stop. We do not have any decision aspect after the decision. We just need to perform a series of experiments that we've decided and then possibly result something. Here we have a priori knowledge about it, of the possibility, and then we can try to experiment to verify, to, for example, get to the level of, okay, it's enough. On the other hand, if we go from the different side, we get series of all successes, let's say 7 trials on 7 with water, it is still possible that the planet is not covered in water in totally, right? So again, the question is it relevant to sample it again? You understand? So this is one of the conceptual advantages of Bayesian statistics, that our model allows us to expect the unobserved. We can expect situations that were not experimentally confirmed yet, but they are still possible. If our prior knowledge assigned them some kind of probability, we can still assess how the data supports that. If the data is completely against that, not an issue. This will just probably will be vanishingly small, and we won't cover that. So when we will, for example, be computing quantiles, that won't matter. But still, the result here is that we still are prepared that our model can recover from getting a series of data that are supporting one of the results and not another. Questions? Okay.
So when to stop doing research?
Oh, well, it depends on multiple conditions. Budget trials, for example. For example, you have budget for 100 trials. And after, let's say, 20 trials, you see that the probability of that from your model, in this case, this very simple model, and the probability is so small that you cannot justify those trials, right? This is a decision process which has certain considerations. For you have limits. Maybe it will be better to fly to different planets and look for water, right? This is the general idea here, that you can, depending on your situation, if test is very cheap, on the other hand, you cannot get 10,000 of tests and no problem, right? Because they are cheap, so there is no issue of doing that. There's no magical threshold. There is some of the literature of classical statistics uses the 5% p-value. This is very arbitrarily chosen by Fisher in the 20s and had no justification. One should do 5% or 1% or whatever it means generally. And it shouldn't be a decision factor. So there is no situation that you just need to know your constraints, know your situation, decide, you can estimate the budget results, and then decide. Experiments were cheap. We are not moving anywhere because we are refueling or something. Or we can try again and do 10,000 tests and no problem, right? We have to try up to success, or not. The experiments are so expensive that we are just not doing it anymore because it's better to try somewhere else.
Okay.
There are no easy answers. There are no universal answers. That's why there's difficulty in applying statistics, because decision process is not binary. Except you are on the fire, use a extinguisher. This is a simple problem, right? but I'm reading currently a book about nerve agents, the sarin, stuff like that. Like there are medicine that helps you to overcome the exposure to sarin. This is called, generally sarin binds with certain substances in a human organism which damages the nerve system. But you can, and this bound is permanent. However, you can use a substance that will bind with the same substance, but this bond won't be permanent. But at the same time, it will stop sarin from binding with those molecules. So generally, let's say you block the outputs with something that you block the sockets that can be attacked by sarin by something that can be removed later. Sarin would block them, but they would block them permanently and will be permanent damages. But those substances are some of them are very their time of work is very quick, very brief. So they will just lose their effect for some time, and they are not, let's say, neutral to the organism. So providing such medicine that gives a risk to the soldiers before using it, while not necessarily there's a probability that they will encounter hostile nerve agents. So in that situation, you need to decide what is the probable best cause of action. What is the decision what is less costly? Potential damage to the soldiers from the treatment or the risk of exposure to nerve gases. So this is the balance that you need to have a decision, your own utility evaluation, what is the most important. Okay, interval summaries. If not number, then an interval. The interval, the easiest interval of course is like mean plus minus standard deviation. This is the most frequent one. You find, for example, in the literature that generally whenever you get something plus minus 3 or something like that in literature, this usually is one standard deviation. So 67% of results is in this interval. So the central interval is based on the idea of symmetric interval around certain variable. Different idea is the highest posterior density region, or highest posterior density interval, which is the interval containing the smallest interval that contains the desired probability. Of course, this is interval, so it is focused on one-dimensional distributions. But it can be also used for marginal distribution. So if we marginalize all the parameters and we are left with one, we can still use that. And we can compute it in different ways. You can, of course, use integrals. Usually it's done by sampling. This is the automatically selected, like you give me 94% of probability, and the algorithm will find it from the function. Also, we can use interquartile intervals. So for our example, if we wanted 94% probability, it will look something like this. This is the highest density interval for the resulting binomial distribution. So as you can see, it covers most of here, and it can cover the unsymmetricity, because as you can see, this distribution is not symmetric, it's a bit skewed to one side, right? So this is a good indicator of our values. However, it has certain limitations, because here we have very simple unimodal distribution. Unimodal, one maximum. However, if there are more maximums, there are certain issues. Because if we get some kind of, if we do not take this the modality in the focus, it will look for a central interval that will get you the lot of very low probable values, right? Here. It will capture something that won't happen. It's like using mean to evaluate the income of people. There is like a lot of people that are earning very below the national mean, and there is like family of late young Burczak, right? Who are moving So generally, our income distribution is multimodal and a bit heavy-tailed because it has a big moat around people that are earning well below the mean, and there's a smaller maximum somewhere in like those high-earning professionals, like in IT and stuff like that, and then you have the heavy tails of very rich people that can happen with significant income. So like this is a modified logarithmic distribution. We can say that, and that's is not that terrible descriptions. But this is an issue with multimodality, and in case of multimodal distribution, if you know that you have such a situation, there's an option of disjoint intervals that will divide the area only to the area. So you will get two intervals that most probability is either here or either here. This is a nightmare for decision makers, especially in business case. If you give the, let's say, head of the company information that, let's say, we have 30% of total loss and 30% of total success, he will be very pleased, for sure. That you give him two intervals that give you the most possible results, but they are separate and the possibility in between are limited. And how do you make decisions? Because when people want like some kind of continuity here, and you have no continuity, you have breakage here. But it's a much better factorization that there is no need for looking for values here. Values here just won't happen, right? So this is this issue. So is everything clear at the moment? We told about binomial model, how it works, what is the likelihood, what is the posterior, that distribution can change completely just from one to another just by changing the look on it, right? We see that Bayesian distribution statistics allows us providing us additional information, and we know how to kinda summarize what we know, right? So let's focus generally on how to put what we know into the model, and let's start discussing about priors. Generally, priors gives us some information about what we had before the experiment or the event happened. So our data collection happened. And there are two general options of looking at priors. The first one is so-called population interpretation. Population interpretation means that the prior distribution represents a population of possible parameter values that what our current parameters are representative for. So like for example, like results of certain, like for example, we assign prior for the parameters of a device that we wanted to use in our system. Then we had previous exposure to those devices with the parameters. So this is this representative of this population. Like for example, factory in China is manufacturing chips. Chips has certain analog parameters that have some variance, and it's confusing. On the other hand, we have a state of knowledge interpretation. The population interpretation is easy when we have repeated situations, right? Especially with a repeated situation we had experienced before. State of knowledge interpretation, we must express our knowledge about theta as its value could be. So this might be very easy, very reasonable, very simple. Like for example, we know for that, let's say there is possibility of problem of heads or tails, right? Or we can add some additional information into that. Either way, state of knowledge interpretation looks as parameters as random variables. Population interpretation looks then like members of population, still like a number. Here it's just full random variable interpretation. Parameters are just certain random variables that we know how they are distributed, and variables come from the distribution, and that's it. So this is more abstract, but on the other hand, it is much easier to understand it in the concept of low frequent events, rare events, or events that didn't happen, right? If it didn't happen, we can still assign some kind of probability to it that it can happen. For example, that's for insurance people. What is the probability that there will be hail and at the same time fire in the barn? So those are events that are low probability, haven't occurred. What the consequences will be, we can still assign some kind of probability to it by using our state of knowledge and representation. Priors can be divided into three main categories. There are different divisions, there are different specializations, but those are the main divisions that we cover today. First of all are non-informative priors. Second are weakly informative priors, and third one are informative priors. So like generally a simple thing. Non-informative prior are generally a piece of history. Because non-informative priors were made for people that were doing Bayesian statistics, where still people are arguing that Bayesian statistics makes no sense, and they wanted to, using Bayesian, get the same results that were given by the frequency statistics. So they wanted to, we remove all the subjectivity. We use Bayesian statistics, but our prior does not introduce any information, or almost only information that is available. This is so-called maximum entropy approach, that you find distributions that only are consistent with the knowledge that you've given it, for example, mean and standard deviation, and that's it. Nothing more is given, so find the maximum entropy distribution that works. So we wanted to express the full ignorance of the matter, and it usually results in bad things. Bad things that give you the posterior distribution that are hard to explore, that have numerical issues, and really no benefit is given here. Because the benefit of the prior is that it still provides certain structure. So why use priors that do not provide structure? So in practical approaches, non-informative priors are non-existent. Different stuff is with weakly informative priors. Weakly informative priors is the priors that, first of all, are probability distributions. This is important, so-called proper priors and improper. Not important, but it happens in literature, so you should know. Improper prior is a prior that is not probability distribution in the sense that it might not integrate up to 1. It is not as bad as one would think, because it might happen that posterior and that the posterior will still be proper, so it will integrate to 1. The multiplication of improper prior and likelihood will give you a good result. One of the examples is so-called Jeffrey's prior, which is the prior, the non-informative prior for standard deviation, which is 1 by sigma, which you should know integral of it is an infinity. So it diverges. So it is not a proper prior, but still it can be used in computation, and after multiplication you get the good results. But weakly informative prior is always proper. Those are improper. So it's a real probability distribution which does not introduce much information, but provides certain structure, generally some kind of regularization. Like, for example, we know that, well, we don't know what the value of parameter will be, but the parameter corresponds to temperature. So temperatures above 1000 degrees and below 100 degrees are very improbable. So let's put a normal distribution with mean somewhere in the middle and a very wide standard deviation. So this distribution will just keep us away from very improbable events, but would not influence our inference inside. Okay? So in this multiplication there are like mostly not much is happening, but still it moves us away from the extreme values. Those are weakly informative priors, and we discuss them especially when we have some kind of prior knowledge, but we might not want to bias ourselves by adding too much. If we know too much about certain phenomena that we want to consider, then it might be difficult to do. So maybe non-informative prior would be better. This is the point of the most subjectivity here, because those regularizing priors are models. However, regularization is generally used everywhere for computation. For example, lasso regression is used for it, ridge regression. This is all has correspondence to the weakly informative priors. There are two ways of making weakly informative priors. Either you make them by making complicated informative priors weaker, so diffusing the information, or you take a non-informative prior and add a bit of structure to it. So it behaves similarly, but it's still okay. So for example, such prior is an option. That's it at least proper because it integrates to, you can put a constant so it will integrate to 1, and it provides you, it maybe doesn't allow such big numbers because it will vanish quicker to 0, but it still allows you a bit of. And we go to informative priors because they introduce information. We know something from previous experiments, we know from earlier results. We can introduce certain constraints that we know that are hard constraints that cannot be moved. Like, for example, water level cannot drop below because the systems will stop it, or we know that we cannot observe more values than this because it will saturate and stuff like that. So informative priors give us the interpretation of being previous information, and are generally can be very useful, but again with certain risks that if we put informative prior that is not necessarily relevant to our case, because we had the prior that we have prior experience with similar thing but not similar enough, that might be a problem. That's why sometimes it's better to use weakly informative prior and then move consider it how it works with different situations. So, in case of binomial example, we can consider the following prior distribution that corresponds to the previous experience. In binomial example, we have successes and failures. Using beta distribution, we can represent our previous knowledge exactly this way by using distribution of prior distribution beta using with points alpha and beta. It will gives us the information about alpha minus 1 prior successes and beta minus 1 previous failures. So this is way to introduce information about the past to our binomial experiment. We did already so many trials. This is in a way very advantageous situation because this posterior has a closed form. By multiplying two beta distribution by themselves with the same parameter theta, we get theta we get the beta distribution with just a sum of coefficients. So using this form, we get the beta distribution with parameters alpha plus y and beta plus n minus y. And again, this gives us, we can compute expectation, and this expectation has a very interesting aspect, as you can see here. This expectation has a form that will take values between the sample proportion and the prior mean, depending on what is bigger, or not what is bigger, but depending on the number of samples in both cases, so either n or alpha plus beta, depending on the situation, one part will dominate. In case of beta distribution, our sample is number of successes and failures. So it will be alpha plus beta plus 2. In case of our experiment, our sample size is n. So our expectation will always lie between either prior expectation or the sample expectation. If we have a lot of data, we will move towards the divided by n. If our data is scarce, the influence of prior will be significant, right? And here we have a very specific situation that I want to cover. It's called something called conjugacy. Because as you can see, we've used beta distribution as a prior, and we got a beta distribution as a posterior. Generally, something like that is called conjugacy. Conjugate prior distributions are such distributions that, when used with certain likelihoods, they will result with posteriors that are the same class. So, for example, when using beta distribution for binomial likelihood, we get beta result. If we use normal likelihood and normal prior, you get normal result. It won't happen in many situations, but for certain probability distribution, there exists certain conjugate priors. The advantage of conjugate priors is that because those distributions are already known, then we can use formulas for their expectations, medians, and so on. And that's the main advantage. Also, because those distributions are known, we also, for example, for scalar distribution, know their cumulative distribution functions, which are very easy to create samples from those distributions. So, it is very easy to sample from a known distribution which you have formulas of very well investigated. This is very easy thing. If and those are advantages because it can make computation dramatically faster. If you can reduce your computation to computation on conjugate priors, the entire problems of Bayesian computation is very simplified. However, it is very rare that conjugate priors really represent our state of knowledge. We can sometimes approximate our state of knowledge with conjugate prior to get some result, but most of cases of using conjugate priors is because we have conjugate priors. With beta here, it's actually natural, but in most cases it's not. If you have no justification for a parameters to follow normal distribution as a prior knowledge, then you shouldn't use this distribution, just like that. So it should not go by itself to use conjugate priors just yet. Okay, and we'll finish with a brief example with 5 slides. But I'll be quick. This is again a problem with binomial likelihood. Problem considers the biology of something called Placenta Previa. This is a medical condition during childbirth when the placenta, the part that connects the baby and umbilical cords to the mother, is moved to the front during the birth. This is that's more or less complicated childbirth complication. The studies gives that that was considered gives that of 980 births, 437 were female. And the question is the proportion to verify, is this a good enough indication that the proportion of girls born with placenta previa is different than actually in this case lower than the proportion of actual girls born in all births. Of course, in the aspect of uniform prior, this is very, very simple. As you can see, we can get the highest density interval that locates us here. So 95.4% gives us the result that it's lower, right? This is relatively easy to compute. And we can also use, also compute it with using conjugate priors. What here is simple. But we can now use some prior knowledge about our previous situation. So the general population. General population, we know, has a girl birth rate of 48.5%. We can easily compute parameters alpha and beta of beta distribution in order to represent the have the same mean. We will now then have one varying parameter alpha plus beta, the population size. So if we get the population, we can change the population size and see how changing the population size will influence our inference, assuming the same expected value for the prior. And changing the population size by orders of magnitude, starting from 2, then 10, 100, 1,000, and 10,000. As you can see, the posterior median is being drawn toward the prior median. Here with our prior has less samples than our population of experiments. Yeah, right? Because we had 980 births, here we had less. So in this case, data dominated. Here we have a balanced situation. We have similar amount of samples and a similar trials in prior. Here the prior is much bigger. So in prior, if prior data is much bigger, then, and again here is question: is this information even relevant to adding to this case? Because generally we know that the bigger population, so if we add so much bigger population, we just obfuscate our data. So we hide our data. And as you can see, the intervals are also moving right here. And we can see it more graphically here, that when we change the prior population, here on those vertical lines, you have the sample average and the mean of the prior, right? And as you can see, if we had a uniform prior, then of course sample average is here, right? With the plus 1 in the denominator and in the numerator and plus 2 in the denominator. But sample is so big that it doesn't matter. It doesn't completely vanishes anyway. And here we have a mean of the prior. When, as you can see, if the prior is of the population of small population, then of course mean is here, but we move towards slightly. If the population is bigger, then our data is being drawn strongly to our prior information. Understandable? Generally, our Bayesian results are a compromise between data and prior. If prior is too informative, in can dominate our data. However, if we have no data, the prior is the only thing we have. So we need to balance what kind of information we've added to that. And one last slide, what about a non-conjugate prior? What if we use different prior? Let's say, for example, we use a normal distribution with the same mean and even with the same variance, because we can. And as you can see, results will be identical with beta for population 1000 and corresponding normal distribution, at least visually. The problem is this is no longer conjugate. So we don't have formulas for expectation, median, we don't have any formulas. We haven't changed the thing, but we've lost the conjugacy. So the matter is, if conjugacy is such, let's say, fragile thing, shouldn't we cover it? Not really. Let's focus on sampling, which will start next week. Are there any questions? If there are not, so thank you very much.